And whenever we graph a quadratic function, we'll always get this U-shape graph called a parabola, we'll see. So let's start off with our most basic quadratic function. Now, we're going to see lots of shortcuts and make lots of generalizations. And the whole key is that a function's graph shows us how the graph behaves or how the function behaves, all right? So it gives us a picture. And you know the old saying, a picture's worth 1,000 words or a million words with inflation maybe, I don't know. But a picture is very valuable. So it gives us an idea of what is going on. Okay, so let's do some evaluating here. So whenever we have a function like f of x equals x squared, that is our most simple function. This is actually what we'll call the parent function, because all quadratic functions will behave like this most basic function, f of x equals x squared. All right, so we're going to evaluate this. Now keep in mind, this is function notation. This does not mean f times x. This means we're going to take, and we want to find f of -3. So we're going to put -3 in parentheses in place of x. We're going to substitute, and we'll evaluate that. That equals 9. So when x is -3, y is 9. And what about when f is -2? Well, when f is -2, we get -2 squared, and that is 4. And we can continue on like this, all right? And this is what we call a table of values. F of -1 is -1 squared, and that is 1. F of 0 is 0 squared, and that is 0. All right, so on and so forth. F of 1 is 1 squared, which is 1. F of 2 is 2 squared, which is 4. F of 3 is 3 squared, 3 to the second power, which is 9. All right, so after we evaluate all of these, we plug in x, we get these y's. Now keep in mind, you can do this for any function. We're going to talk about lots of shortcuts, lots of patterns, but you could always make a table of values. This always works, okay? Now we're going to find lots of shortcuts and make generalizations, but you can always plug in x values and find y values and graph points like we're going to do. The only problem is sometimes you're not going to know which x values to plug in. It's kind of hard to find. You'll have to hunt for a while. So anyways, we got y, our x-axis and our y-axis. Remember, y is the same as f of x. All right, so we're going to plot these points. So we've got an x-coordinate and a y-coordinate. So this represents the point 3, -3, +9. All right, so these are all coordinates. -3, +9. So let's get, it's a good idea to label at least one number on each axis. When we put 5 there, we know that means 1, 2, 3, 4, 5. We're going by ones, all right? So it's a good habit to be in. We often get out of that habit. Okay, but we'll label that. You don't need to label every single number, but all right, -3, 9. We're going to go left 3, up 9. And there's our point right there. Then we have -2, 4. So we're going to go left 2, up 4. Then we have -1, +1. Then 0, 0. Now we're in the positives. So +1, +1. It's going to be right here. And +2, +4. And +3, +9. There it is. All right. And that's a 10. All right, so these are some points. Now, there's lots of points in between. If you really wanted to, you could plug in a 1.5 and you'd get a point right about here. You could plug in 2.3 and you get a point somewhere up in here. But we don't need to, because we know that mathematical functions behave well. They follow nice patterns, and so it'll continue in this manner. So we find 5, or in this case we found 7 points, it looks like, and it gives us an idea that it looks like this. All right, so this is a shape. This is what we call a parabola. All right, and this is a shape we'll really want to kind of memorize. All right, so notice that a couple things here. It is symmetrical. So symmetrical means the left and the right hand side are identical, even though my freehanded graph here is not exactly the same, but we can draw a line right down the middle that cuts it in half. And that line right there has a name that's called the axis of symmetry. All right. Cuts it in half. Now, we also notice that this graph comes down, it has a lowest point, and it turns around. That point where it turns around is called the vertex. And that's the most important point of a parabola, is the vertex. We'll be looking for that. Notice that the vertex lies right on the axis of symmetry. All right. So there's some key features there. All right. Now notice this. What are the coordinates of the vertex of this graph of f of x equals x squared? Well, it's at 0, 0. So it all starts at 0, 0. And then what's the axis of symmetry? Well, this is a vertical line. There's an equation. The equation of a vertical line is the equation x equals 0. That is the equation of that vertical line. It's describing a line. That's a linear equation. Okay. Well, let's explore a little bit. So that's a simple y equals x squared, or f of x equals x squared. But what if we throw a number in front? What if we have like 3x squared, or 1/4 times x squared, and so on and so forth? What's going to happen? So we're going to go to our graphing calculator, or Desmos, and graph this and just see what happens. All right. So let's come down here and we'll do some exploring. We'll graph y equals x squared to start. And so y equals x squared. There it is. There's our parabola. Notice we've got the point 0, 0, 1, 1, 2, 4. Okay, so those are important points there. In fact, I'll go ahead and enter those points there. So there they are. Okay, we'll keep those in mind there, right? Notice that relationship with those 5 points. Want to get real familiar with those 5 points. All right, well now what if we change this? So let's go ahead and get a new equation now. We're going to graph y equals not x squared, but 3x squared. So we have y equals 3x squared. Oops, I didn't get my 3. There it is right there. So the blue one there is 3. So notice it gets a little skinnier. So it's going to be kind of steeper or skinnier. Or actually, we'll say it's kind of a vertical stretch. So we call this vertical stretch. It's like this red one, which was our parent function, is pulled upward. All right. So this point that was right here is now pulled up to here. This point that was at a height of 1 is pulled up to 2, or actually 3. All right. What if we change that to a 1/4? Well, if we have 1 divided by 4, there it is in blue there. So if we have 1/4, it gets a little wider than our regular y equals x squared. Okay? Or we say this is vertical shrink. So this point that was up at 1 is now down here. This point was up at 4, now it's down at 1. All right? And if we change that 1/4 to a 1/10, well, 1/10, there it is. It's even wider, or has even more vertical shrink. So it goes up slower. So as it climbs, it's not as steep, has less rate of change, we can say. All right. So that number in front, if it's getting smaller and smaller, getting closer to 0, 1/10, 1/30th, 1/50th, it's going to be a lower rate of change here. All right. So vertical shrink and vertical stretch is the words we use for that. All right. Now, what if we take that number in front and we'll get rid of that 1/10, and let's make that negative, or really -1 if you want to think of it as that. So negative x squared, what happened? Well, it flipped upside down there. All right. So by entering -1, we got an upside down parabola. Now notice the shape is exactly the same as y equals x squared, but it flips. All right. So it's reflected across the x-axis. Okay. What happens if we make that a negative 3x squared? So let's take that -1 and let's make that -3. Okay, well, it got skinnier. Again, it flipped because it's negative, but it stretched down. So it's the mirror image of this 3x squared here. So 3x squared is this one. It's steeper, or it's vertically stretched. This one is steeper again because of the 3, but it's upside down because of the negative. So can you think about what this one's going to do? It's probably going to be the exact opposite of this, right? And that is what's going to happen. So if we have negative 1/10, negative 1/10, there it is. So it's flipped upside down, and it's wider than the standard y equals x squared. All right, so now we've got kind of a general feeling of what happens. We always get a parabola, but that number in front, we'll call that the a value, all right? So we'll use a to represent that number. That number is also called the leading coefficient there. That leading coefficient is what changes the shape of the graph. So now we can generalize what happens when we change that a value. So if a is greater than 0, the graph opens up. We say this opens up. The graph will be, for positive a value, will open up like this, kind of like y equals x squared. If it's a negative, then it will open down. So if a is less than 0, it'll open down. So this is like y equals 1x squared or 2x squared or something like that. If we have y equals negative x squared, well, that's going to look more like this. And it's going to open down for negative 1 or negative 2 or something like that. Now, if a is less than negative 1 or a is bigger than 1, so if a is bigger than 1, like 2, 3, 4, 5, or negative 2, negative 3, negative 4, negative 5, then that graph is going to it's going to be half as steep as y equals x squared, or we say this has vertically shrunk. So to start off here, let's go ahead and let's think about the points of y equals x squared. We graphed those earlier, 0, 0, 1, 1. Zoom in here, and 2, 4, negative 1, 1, negative 2, 4. Before I go any further, I should mark some axes here. I should label my axes. So if we're going by ones, that's good enough. All right. Now, so if that's y equals x squared, well, y equals 1/2 x squared will be half as steep. So let me just kind of lightly put in y equals x squared. That's That's our reference here. So this is called our parent function. So we should have that in our mind, even if we don't kind of lightly sketch it out. So y equals 1/2 x squared. Well, it's going to go up half as high. So it's going to be at 0, 0. It's going to go right 1. Instead of going up 1, it's going to go up half as high. Half as high as 1 is a half. Then we're going to go 2. And instead of going all the way up to 4, half of 4 is 2. So we're only going to go up 2. And the left side is going to do the same. Up a half. And then we'll go left 2, up 2, not all the way up 4. And so those points right there give us a pretty good idea of what our graph will look like. If we want a better graph, we will go to our calculator or our computer. All right. So that red graph, that's our final graph there. All right. Now again, we can always crank out points. So don't forget, you can go to your table of values and plug in 0, and this is going to be plug in 0, 1/2 times 0 squared. So 1/2 times 0 squared is 0. Plug in 1, 1/2 times 1 squared. That's going to give us a half. So when you plug in 1, you get a half. Plug in 2. When you plug in 1/2 times 2 squared, well, that's going to be 2 squared is 4, and half of 4 is 2. All right, and those are the points that we got here: 0, 0, 1, 1/2, 2, 4. 2, 2. All right, so we can plug those in, and then we get they're symmetrical, so we can go to the other side here, and we can find that. Okay, now, so that's the a value, which determines the shape. Next, we'll go figure out what happens with the other numbers that we can add into the equation.